Log on, tune in, find out. Another good idea from Cambridge.
This afternoon's Ernesto Mistretta, who's going to talk on linear stability and stability of dual span bundles.
Okay, so first I would like to thank a lot Peter and Letizia for inviting me here. It was an invitation at the very last moment, so I am very pleased to be here. And what I'm going to talk about is a work that is still very much a work in progress and is a joint work with Lidia Stoppino. So I'm going to try and explain the setting and the question that we posed ourselves and give some of the results and the methods used. So the setting is the following one. We take X a smooth projective curve of genus G bigger or equal than 2 over the complex number, and then E a globally generated vector bundle on the curve X, and V a generating subspace of global sections. And then we construct the following exact sequence given by evaluation of sections on V. And we call MVE the vector bundle that arises in this sequence. So this is well known and much studied in the literature, and mostly the stability of this vector bundle is appears in the literature in many cases. So I should try and give some of the examples in the literature. I think the stability of bundles like this in the first time were studied by Paranjap and Ramanan. And the purposes for studying the stability of this vector bundle can be found in very different aspects in the literature. So from Paranjap and Ramanan, these bundles for the canonical line bundle of the curve were studied in order to make some progress to know the green conjecture. Then these were studied following much or less the same methods for general vector bundle and the whole space of global sections by Butler in order to study normal generation of the vector bundle. And then these were studies in order to construct or to prove non-emptiness of some coherent systems by Peter Newstead and Letizia Brambilla Paz and Bosley and many other people also mainly in this audience. But these were studied also by Hein and Lazarsfeld in order to show stability of the Picard bundles on a Jacobian of a curve, and by Beauville in order to study theta divisors, and by Popa in order also to study the existence of theta divisors. And every time, I mean, many times, these are called in different ways in the literature, so I should say this as well. These, for example, these, usually they are called dual span bundles, and sometimes, at least when I started studying these, it was for other purpose, for questions of generation of Chow rings, and I didn't know much of the literature, so I called them transform of line bundles or of vector bundles, as they can appear in somehow as a Fourier-Mukai transform. And these are called, I think, CGG bundles by Hein and Lazarsfeld, and these are called Lazarsfeld bundles by Popa. So they appear in with very different names, but they are a central object to study. What I will consider today are questions related to Butler's conjecture. Which I can state in the following way. If we consider X a general curve, then if we take E stable and general as well vector bundle with a generic subspace generating of global sections, then first thing, this most general condition imply that the vector bundle MVE is stable, or at least semi-stable. And the second thing, this construction gives a birational correspondence. So we obtain a birational map between the following spaces, which I will try not to define precisely. So the space of stable bundles of rank E, of rank, let's say R, rank E, degree E, and generated by some space of dimension dim V, through this map, considering the dual of MVE, should be birational to the space of stable and generated rank dimension of V minus rank of E, degree E, and generated by a subspace of dimension of V, and this correspondence should be given by considering the couple EV and associating to this the bundle MVE dual and the generating space V star. So, of course, these spaces must be taken properly, and also the generality of the vector bundle should be taken properly, and in order to have a moduli space, also the stability of this object should be considered in a proper way. But I will talk about only the first part, so the stability of the vector bundle, of the dual span bundle MVE. And I should say I cannot list all known results, but at least the sum of the let's say easily stated results are the following one. The first one is that if E is stable and the slope of E is bigger than 2G, and the space is complete, so we take the whole space of global sections of E, then the dual span bundle ME is stable. So this is a first result. Then, as I'm going to look only the rank 1 vector bundles, so line bundles in the place of E, in the case of rank E equals to 1, then another, and in the case of generality as stated here, another result is the following one. If we take the degree of E in the following range, so between G plus dimension of V minus 1 minus the integral part of this number, G divided dimension of V, and G plus dimension of V minus 1. Okay, so in this case we have stability, and as well in the case D smaller than 2 times dimension of V minus 1. So these are some of the known results. Yes?
About the statement of the conjecture, you put general curve and general bundle. So does it mean that for every curve there is some counterexample?
No. I mean, this is just a conjecture as stated. Doesn't mean that you don't need, I mean, that if you have a non-general curve, then you, even because generality is not not always. I mean, you cannot take a curve and say
So
this
why
is a
why
not
is
general
the
curve.
conjecture that for every curve for general bundle or for something like that?
There are examples for. Yes, I mean what you mean is that you could choose.
For there are examples there for any curve there exists bundles that doesn't satisfy.
Yes, but I mean you have to consider bundles and some given subspace. So the generality I just stated in the most general case because this is the way one can try to show results in this way. Then yes, I mean I will try to show also some results where you don't have stability, but always for non-general vector spaces. So this is why I was saying the generality should be considered in the proper way. Okay, so this is the conjecture. This is some of the known results. What I want to try and talk about today is the relation about the stability of this vector bundle and something which is the linear stability of a line bundle. So it's another stability concept, or let's say still coming from GIT, but related to line bundles. So I will give the definition. Definition of stability on curves is let's say the easiest case, but I will restate what this definition is. So if we take any vector bundle on a curve X, we say that this is semi-stable or stable, or mu semi-stable or mu stable, if it is stable with respect to the slope. So if we consider any proper subbundle F, we have the slope inequality, so the degree of F divided by the rank of F should be smaller or not greater in the semi-stability case than the degree of E divided by the rank of E. So this is the mu stability, and then for line bundles and linear systems we consider the following definition. If L is a line bundle on X and V in the space of global section of L is a generating subspace, then we say that the couple LV is linearly semi-stable or linearly stable if for every proper subspace V prime in V, if we call L prime the image of V prime in L, so we have the following slope inequality, which is the degree of L prime divided by dimension of V prime minus 1 should be greater and greater or equal in the semi-stable case than the degree of L divided by dimension of V minus 1. So this is the definition of linearly stable and linearly semi-stable. So this definition, I think it comes back from Mumford, and Mumford and also Gieseker proved that linear semi-stability of the couple LV implies Hilbert stability of X and L and V. So this is the reason it was defined, because usually Hilbert stability of even for a very ample and a complete linear system, linear stability can be harder to prove then Hilbert stability can be harder to prove than linear stability. Some remarks. The first one is the following one. Maybe we'll try. So, given any subbundle Q in MVL, we can construct the following diagram. We have this subbundle in MVE, and we can place it in an exact sequence in this way. Okay, and here we take the space W is defined as by its dual, which should be equal to the image of this star in H0 of Q star. So W is generating Q star, and so F, what we will call FQ in the following. FQ is a globally generated vector bundle with no trivial summands. Okay, so this construction, I think this as well, it comes from Butler's proof. So the first remark coming is that in particular when we start from a line bundle and we consider a subspace of global sections, so we have, if we have L and V, where V is a generating space and V prime is in a subspace of V, we can fit the exact sequence defining MVL on an exact sequence. In this way, with the only difference that in this case we have that the bundle FQ is a rank 1 subbundle of F prime, while here we can only say that we have a non-vanishing map. But so, in particular, if MVL is semi-stable or stable, it follows that this must be of smaller slope, and so it follows exactly the inequality defining linear semi-stability for L and V. So if MVL is semi-stable, we have that the slope of MV prime L prime, which will be equal to minus degree of L prime divided by dimension of V prime minus 1, should be smaller than equal than the slope of MVL. So if this is stable, we have that LV is linearly semi-stable. Okay. Second remark, we can rephrase, so the linear stability of L and V using this diagram, saying that the subbundle MVL cannot be destabilized by any the bundle MVL cannot be destabilized by any vector bundle Q that arises as a dual span sheaf of a rank 1 vector bundle FQ. So linear semi-stability. Just another way of saying the same thing is that So we have linear semi-stability if and only if MVL is not destabilized by any Q such that the rank of FQ is equal to 1. Okay, so the question that we tried to answer is the following one. In which case can we say that linear stability or linear semi-stability is enough to imply stability of the dual span sheaf? So the question is the following one. Let's say, when can we deduce stability of the dual span sheaf MVL knowing only linear semi-stability of the couple LV. Okay, so this was the question. In the end, I will try to to show with a simple example that this is not always the case. But the question was, if we want to know something about the stability here, and we know that a destabilization cannot hold when the rank of this is 1, can we manage in somehow to show that the destabilization cannot hold in general? So, which were the motivations for these questions? The first, let's say, the thing that triggered the question was the following one. We have, and so this started from a work of Barja and Stoppino that comes from the following consideration. Let's say, so the first is the following thing. There are some analogies between the, let's say, linear, or let's say, analogy between different concepts of stabilities. So, different stabilities appear in works, in some works which are one by Kornalba and Harris, another one by Xiao, and a third one by Moriwaki. So these are results obtained in different contexts, but let's say that they can pass, following the proofs, they obtain a proof of some slope inequalities obtained passing through stability. So this, in the context we want to see the analogies, these slope inequalities, they arise from calculating the following inequality for a fibered surface on a curve. So let's say S smooth and projective surface and F fibration in the sense of having connected fibers of genus greater or equal than 2, and F relatively minimal, then the slope inequality is the inequality relating canonical bundles and characteristics. Okay, so this slope inequality arises in different contexts in these three works, but what we can say is that Cornell-Binaris use Hilbert stability for the canonical bundle on the curve, on the general curve. Then Xiao uses linear stability for the canonical bundle of the curve, and Moriwaki, I mean, we cannot say that he uses stability, but what we can say is that following exactly the same proof given by the authors for maybe different inequalities, we obtain exactly this same inequality in this context using these three different stability ideas. Then knowing what we just stated, of course, the linear stability for the canonical bundle implies Hilbert stability, and the stability of the dual span bundle of the canonical bundle implies linear stability. So, but what they remark and what Bargia and Stoppino use in some particular cases and are using in a work in progress in more general cases is the comparison of these three different methods. So this, at least, this triggered the question, when can we deduce, for example, for the canonical bundle, can we deduce in general that we have some equivalence between linear stability and slope stability for MVL? Then other motivations.
Excuse me, sorry. Are you saying that you can prove that inequality without going through the Hilbert stability of the curve, like a direct proof? Or does it use this remark on the...
No, I mean, I think that you can conclude the inequality, yes, but I haven't read carefully the paper. I think this is the object of some recent work of Bargia and Stoppino to deduce the inequality directly. Okay. Directly from linear stability on linear semi-stability on some linear bundle, some line bundle. Okay, so this is just to mean it is worthwhile considering when linear stability is enough also to deduce some properties of the dual span sheaf. Then other motivations lie in the fact that some of the results obtained in the case where E is a line bundle to prove stability of this dual span sheaf, in somehow looking through the proofs, they go through the proving on a side that a destabilization cannot come from something of rank greater than 2, so proving linear stability for this for the couple, and then on another side proving, for example, in some cases using only general spaces of generating sections, then proving that linear stability hold for the couple. So in some cases one can see that this is a good strategy to show stability of this object, and the hope is that maybe we could have a better understanding also in the higher rank case to try and show in which cases Butler's conjecture hold. So these are the motivations. The objective is the following one. At first, it seemed reasonable to ask whether the following condition on the degree of the line bundle is enough to have an equivalence between linear stability and stability of the dual span sheaf. So the initial objective is the following one. It seems reasonable in the following case, if X is a curve of genus G greater than 2 and gonality gamma, if we have a line bundle and a generating subspace may be general. That verifies the following inequality: the degree of L divided by the dimension of V minus 1 smaller or equal than gamma, then linear stability implies, or linear semi-stability implies, stability of MVL. So within this restriction, we were hoping to obtain equivalences of the two stabilities. The results so far allowed us to show some equality on a way smaller restriction, or a stronger restriction, way stronger restriction than this one. So we can resume this in the following one. So if we have that the degree of L is smaller or equal than the Clifford index of the curve plus 2 times dimension of V minus 1, and one of the following holds: so either we have a complete linear system, so V is H0 of L, or we have the degree of L is smaller or equal than 2G minus the Clifford index of C plus 1, or we have the opposite inequality: degree of L is bigger than 2G minus Clifford index of C plus 2, and we have small codimension. The codimension of V is bounded by H1 of L. Or if the degree of L is bigger than 2G and the codimension of V is smaller or equal than degree of L minus 2G divided by 2, so small codimension. In these 4 cases, then we can conclude that linear stability is equivalent to slope stability. So then LV is linearly semi-stable if and only if MVL is semi-stable. So remarking that the ideal bound was degree of L smaller than the gonality times dimension of V minus 1, this is a way stronger condition. And let's say it's not very satisfying, but it allows already to have some corollary. So first we have the following result. If the degree of L is smaller than Clifford index of C plus 2 times H0 of L minus 1, for example, if L computes the Clifford index, then MVL is semi-stable And furthermore, it is not stable only in the following case. So it's always stable except the following case. It's not semi-stable if and only if we are in one of the following cases. The first one is that L is the canonical bundle of the curve times an effective divisor of degree 2. In which case one can prove that it's not stable easily. And in the other case, if C is hyperelliptic, then and the degree of L is exactly 2 times H0 of L minus 1. So in these cases, we have semi-stability but not stability, strict semi-stability. And well, first we have to say that we were somehow happy about this result because this does not consider only general curves, but relates some stability properties with the Clifford index in, let's say, the natural idea that the more the curve is general, so the highest the Clifford index is, the higher stability properties it should have. We realized as well that I think the very same statement is contained in Paranjape PhD thesis, but it was never published, so I don't really know if it was published. And second thing to state is that I think in case of computing the Clifford index, also these results are contained in Brambilla, Paz, and Ortega work on stability of this dual span sheaf and on coherent system for special curve. So here we have to put in the inequality we have H0 of L, so it's the complete linear system. And in order to prove this, one has to prove the simpler case. So one has to prove linear stability for the couple L and the complete linear system H0L, which follows easily than showing stability. So this is the way one proves the corollary. Another consequence of this is something that's in the same flavor of the stability for general curves, just a simpler way to write this. So another corollary is the following one. If the degree of L is bigger or equal than 2G minus the Clifford index of the curves, and L is globally generated, then M L with the complete linear system is semi-stable, and it is even stable unless one of the two conditions hold. So this, just to give an idea, the bound degree of L bigger or equal than 2G is contained, is part as the result by Butler on vector bundle and by Ein-Lazarsfeld on line bundle. So it's known. The fact that one can improve the bound using the Clifford index corresponds to that behavior of general curves. Okay, so what are the methods we followed in order to prove these results? The methods are the following. It's a simple construction arising from that pair of exact sequences wrote on the other blackboard. So the methods lie on the following consideration. Let's start from generating, let's say, a base point 3 linear system. And let us assume that the degree of L is smaller or equal than gamma times dimension of D minus 1. So as in the objective, as in the ideal bound. Then we consider the exact sequence of the dual span bundle. And let us consider any subbundle Q constructed as in the other blackboard. And let us suppose, so we know that FQ is globally generated. Let us suppose that the rank of FQ is bigger than 1. Okay, so in this case, we have an exact sequence taking R minus 1 general sections in FQ. We have an exact determinant sequence, which is the following one. Let's say if these sections are general, we call R the rank of FQ, which is bigger than 2. Then we have the following exact sequence where A is the determinant of F, okay, if we make the further assumption that this exact sequence is exact on global sections, if this is exact on global section, we can make the following construction. We can construct the following sequence. MA, we tensor the dual span sequence for A with the canonical sheaf. So we obtain a sequence, some resolution of A tensor omega C. And then we have our exact sequence for F, okay, where this is not Q, it's just for the space of global section on F. Okay, and so we have that in the case of a sequence such that exact on global sections, this means that the sections of F surjects in the section of A. So it means that this map is surjective. Okay, then passing to global sections on that diagram, we obtain the following. So taking global sections in that diagram, we obtain the following diagram. The evaluation on global section for A and omega to global section of A times omega, and then the evaluation of global section for F and omega on global section of F times omega. And then we have a commutative diagram where we know that this vertical arrow is surjective, and we can show that this arrow here is not surjective. This is simply by considering its dual, so this gives H1 of A star, H1 of A star, H1 of O r minus 1, and H1 of F star, H0 of F star. Then, as we know that F has no trivial summands in general here, it cannot have global section. Then this is 0, this is different than 0. Okay, so this map cannot be injective, and this implies that this map here is not surjective. Okay, but then if this map is not surjective, it means that this map here is not surjective. So this map here is not, cannot be surjective. Okay, and then it is a result that I used to state as a result of Green, but it is, someone told me it was known already by Castelnuovo, that if you have that this map is not surjective, this means that the linear, the map given by the line bundle A maps the curve to a rational normal curve. So that map here so this means that the map given by A maps X to a rational normal curve in the projective space. Okay, but then we obtain the bound that we want, because this implies that the degree of A, which is equal to the degree of phi times H0 of A minus 1, this must be bigger than the gonality times H0 of A minus 1. So in this case, using only the fact that we have a sequence for F which is exact on global section, we obtain that the Q we started from must satisfy the following inequality. The slope of Q, which is equal to minus degree of A divided by dimension of W minus length of FQ, this must be smaller, bigger, minus, so it must be smaller or equal than minus gamma, which is smaller or equal than the slope of N of M. Okay, so we can resume all this in the following lemma. Maybe I can just state the following lemma. If we have a line bundle verifying this, maybe I just write it. If we have every generating linear system such that the degree of L is smaller or equal than gamma times dimension of D minus 1. If we have Q subbundle of the dual span sheaf for V and L, which is such that it is a dual sheaf coming from something of length bigger than 1, then the slope of Q must be smaller than the slope of NL. Okay, and one can have a little final result, in which case there is only semi-stability, or in which case there is also stability. So what we are saying is that if we didn't say it properly, we are supposing that the exact sequence is exact on global section. So FQ has rank 2, and there exists a sequence which is exact on global section. Okay, in this hypothesis we can conclude that the slope of Q must be smaller than the slope of M. Also, this actually comes from some result of Butler. What we did not succeed is in improving the exactness of global sections for every sequence arising from a destabilization. So all the results I stated basically follow from computing that exact sequence. So they all follow from the following consideration: if the degree of L is inequalities of the result, so smaller than the Clifford index of plus 2 times the dimension of V minus 1, and if the slope is bigger or equal than the slope of MVL, so if we have something which is destabilizing MVL, and if the length of FQ is bigger or equal than 2, then the global section of FQ minus the rank of FQ plus 1 is bigger or equal than H0 of A. So that we have necessarily the exactness of the global section, the exactness on global section of the exact sequence of R minus 1, FQ, and A. So the result, let's say the geometrical idea is trying to obtain results on the gonality of the curve from some exact sequence arising from a destabilization. The problem is that it only works in these cases, and these cases are obtained just by very long calculation involving inequalities. But this is where all the, let's say, pretty much all of the results obtained until now are just based on this exact sequence. And we have to say, in the case we were hoping, so in the case degree of L is smaller or equal than gamma times dimension of V minus 1, if we could always have the exactness of that global sequence, that sequence on global sections, or if we could have the non-surjectivity of that map, this would already imply the equivalence between stability and between semi-stability of this one and linear stability for L. So this is the reason of being for all this computation. I want to conclude with some examples. The following one, a an easy geometrical interpretation of linear stability. That allow us to show also some cases where we have linear stability but not stability of the dual span shield. So, for example, the first one is starting from plane curves. Start from a plane curve, so a curve of degree d in P2, possibly singular. And then if we take the normalization of C0, we have a linear system of dimension 2 on C. So this gives a linear system where T has dimension 3 and L has degree D. Okay, then what we can say is that if C0 has no points of multiplicity bigger or equal than D over 2, so if all points of C0 has multiplicity strictly smaller, then LT is linearly semi-stable, linearly stable, by observing that considering linear stability is actually considering projections from Pn to smaller projection spaces. So this is simply considering that we have any projection must be necessary on a space of dimension 1. Then we have C0 in here, we have our normalization. Okay, then when we look at projection on P1, what we are doing is projecting from any point of P2 onto a line. And so what we have is that if the multiplicity of a point is smaller, of any point is smaller than D over 2, then this projection, we take any projection and not be a map of degree smaller, degree bigger than D minus NP. So it must be bigger than D over 2, which is exactly the degree of this line bundle divided by the dimension of D minus 1. So we have immediately linear stability if this condition holds. What can we do in order to prove that linear stability does not imply always stability? We consider P1, consider a rational, let us consider a rational curve in P2, which is of degree D, let's say degree D odd, and such that the multiplicity of every point is smaller than D over 2. For example, I think with D equals to 5, one can construct such a rational curve. And then we have that necessarily on P1, everything is split. So the exact sequence look like this. And then so if D is odd, necessarily this cannot be a stable bundle. And what we can do is that if we take any covering of P1 and the pullback of the line bundle to the covering, then necessarily the morphism to the projective space is given by this diagram. So again, we have something which is linearly stable, but is not stable. Okay, but the fact is that in all these cases, we don't have generality of the space of global section, and we don't have neither the condition on the degree and the gonality. So you can already wonder, for example, if the generality of the vector bundle is needed to obtain some result in this way, because in all cases it's just a dimensional computation. What one can do is that in general, if we have equivalence between linear stability and stability of the dual span shift, then by taking a generic vector space, usually it is possible by dimension count. I mean, sometimes it's possible to show linear stability. So this is one of the main objectives we have. One more time, the other thing, I mean, just simply following the corollaries, what we can construct is always some roads on the general curve of even genus. We can construct vector bundles, let's say some dual span bundles, and which are of slope -3. And so let's say next thing to do in order to use this result, we can show that this is stable. And one thing we want to do is applying some of the known results or studying the theta divisor for this vector bundle. And another thing to be so this will be a vector k minus 1 and slope 3. So study also all of its tensor powers and studying theta divisor also for the tensor powers. This is something that needs to be done, and it's interesting as these are the bundles used. I mean, in some cases these are the bundles used to observe behavior of the theta divisor. Okay, I will stop here.